Hello everybody and welcome to the second part of lecture 6 of MHM 420-780. So far we have neglected the effect of conduction and convection, so we haven't talked about it. We were just focused on radiation, heat transfer and radiation exchange between two surfaces. But the truth is, in many applications, convection and conduction are as important as radiation and must be considered in the heat transfer analysis. Consider the general surface condition of this picture, as I showed it here. In addition to exchanging energy by radiation with other surfaces of the enclosure, there may be external heat addition to the surface, like electrical heating inside. Or heat transfer from surfaces by convection or conduction. So let's say we have like a surface here, we call it surface 1, and we want to write the energy balance for it. So basically what we say is 1 ext equal to 1 radiation q dot 1 convection plus q dot 1 conduction. We have three modes of heat transfer. It's not necessary that compulsory that we have all the three forms of, but this is the general form. Sometimes you don't have convection, sometimes you don't have conduction, sometimes you don't have convection and conduction, so it's a general form. But what is this radiation here? Basically, it's the net rate of radiation heat transfer. Net rate of radiation heat transfer from the surface, and can be determined from the knowledge that I talked about during the last couple of lectures. Okay. So you might say that, okay, you talked about radiation, we know how to calculate between two surfaces in one enclosure, but how about the convection, how about the conduction? So you passed the course on convection and conduction, so we are not going to speak about it, and that's the reason why MHM 420-780, it's an open book course. It means that you need, the only thing that you need to know is the concept of convection and conduction heat transfer. You don't need to memorize any of those correlations. You can go back to your textbook and find those correlation, put the number inside and calculate. So it's not very difficult, it's very simple, but might look difficult. Let's solve an example together and see how we can use it in reality, because I think after that you will understand how easy it is, and it will be really enjoyable for you. Okay, let's solve an example together then. This is consider an air heater consisting of a semicircular tube for which the plane surface is maintained at 1000 Kelvin and the other surface is well insulated. Let's say this is a surface 1, this is the surface 2. Surface 2 is well insulated. Surface 1 should maintain at 1000 Kelvin. The tube radius is given. Surface emissivities are given. So the property of air is given. So it's asking what is the rate at which heat must be supplied per unit length to maintain the plane surface at 1000 Kelvin. So basically what it's asking is, there is an external heat source at surface 1. We need to find it. Okay. So let's see how we are going to deal with it. First of all, we know that it's a two surface enclosure. Okay, two surface enclosure. You go to page 786 of your textbook. For two surface enclosure, we have one correlation, q dot 1 2 radiation is equal to q dot 1 radiation is equal to minus q dot 2 radiation. So we have this one. Let's write the energy balance for surface 1 and surface 2. So q dot 1 ext external is equal to q dot 1 radiation plus q dot 1 convection plus q dot 1 conduction. The same for surface 2. Q dot 2 ext is equal to q dot 2 radiation plus q dot 2 convection plus q dot 2 conduction. Conduction, we didn't mention it in the question, so remove it. Surface 2 is well insulated, so this one is equal to 0. So basically now we have 3 correlations. Let me just write it down for the from 2 surface enclosure we have this one, q dot 1 radiation is equal to minus q dot 2 radiation. From energy balance for surface 1 we have this one, q1 ext is equal to q dot 1 radiation plus q dot 1 convection. And for surface 2 we said that q2 ext is equal to 0, then q dot 2 radiation is equal to minus q dot 2 convection. Okay, so just look at these two. From these two, what we can say that q dot 1 radiation is equal to q dot 2 convection. Am I right? So we find it, we put this into the energy balance of surface 1, so q dot 1 ext is equal to q dot 2 convection plus q dot 1 convection. Now let's go back to the question and see what is asking us. The question is asking what is the rate at which heat must be supplied per unit length to maintain the plane surface at 1000 Kelvin. So basically is asking for q1 ext divided by L. It's asking give me this number. Okay, so we have it here. Convection, very easy, q dot 1 ext divided by L is equal to 1 divided by L. Convection, 2 convection, so H A2 T2 minus Tm plus H A1 T1 minus Tm. Okay, what is A1? Is 2R0 multiplied by L, and A2 is equal to pi R0 L. So if we add those, L will go away. So basically q dot 1 ext divided by L is equal to H pi R0 T2 minus Tm plus H2O T1 minus Tm. Okay, it's very simple, so we find it very simple. So let's say what we have here. So we wanted to calculate this q dot 1 ext divided by L, so it's what we want to find. Pi Do we have it? Yes. R, do we have it? Yes. T1, do we have it? Yes. Maintain the temperature at 1000 Kelvin. How about Tm? We have it 4000 Kelvin. So the only thing that we need to find here is T2 and H. So the rest are clear. Okay, so we want to find H and T2. So how we want to find the H? So we know that from page 498 of your textbook, H is K Nusselt dH. Okay, so but you see that here K, you might say that, okay, where can I find it? It's very easy. From table A15. Why table A15? Because question gave us something about air. Am I right? Air at 1 atmosphere and 400 Kelvin. Okay, if we go to table A15 by considering those two, we can get some information. K, we can find it 0.0338 watt per Kelvin is equal to 2.3 minus 5. Cp is equal to 9 joule kilogram Kelvin, and Prandtl is equal to 0.69. So those information we find from table 15 that we can use. But let's say, okay, H, we want to find H. We have K. How about this DH? So if you go to page 474 of your textbook, you can see that it's easily is equal to 4 AC divided by P. So easily can be found. So if we have this one as well then. So if we find Nusselt, we will have H. So Nusselt D, from page 517 of your textbook, you can see this correlation. Reynolds D to the power of 0.8, Prandtl to the power of 4. Prandtl, do we have it? Yes. So if we find Reynolds, we will have Nusselt. When we have Nusselt, we will have H. Okay, let's find all of that and see how does it work. Okay. So first, let's find out the hydraulic diameter, DH. DH, I mentioned, is 4 AC divided by P. So it will be 2P RO pi plus 2. Basically is 0.0244 meter. But you might say that, oh, how you get to this point? It's very simple. 4 pi r power of 2 divided by 2 divided by pi 2 plus 2RO. Okay. About the Reynolds D, we know that it's m dot dH AC mu. So we have all those numbers. We have m dot, we have dH, we have AC, we have mu from the table. So the Reynolds is equal to 16,900. So now let's say we find a correlation from page 517 of the textbook. But is it the right correlation? We need to check it based on the Reynolds number that we have calculated. So if you go to page 5.7 of your textbook, it's saying that you can use this correlation for Reynolds numbers more than 10,000 and heating condition. Am I right? Okay, so it's looks like that everything is fine. Reynolds is greater than 10,000 and heating condition. So if we put this Reynolds into this correlation, Prandtl we have 0.69, we can find Nusselt. We have the Nusselt, we have the hydraulic diameter, we have K from the table, we will find H. So let me go to the next. So basically Reynolds is equal to T900, DH is 0.0244 meter. By having all of that, H will be equal, first Nusselt will be equal to 47.8, so H will be equal to 66.2 at 2 Kelvin. Okay, so we have H. The only thing that we need to find is T2 to be able to calculate the Q.1 EXD divided by L. So to find T2, what we need to do? Okay, let's go back to our electrical engineering and the concept of thermal resistances. Okay, from here, if it's Q.1 EXT EB1 E2 EB2, okay, here is Q.2 EXT, we said that is equal to 0. We have Q.2 and convection. Here we have Q.1 convection, R1, R12, and R2. We also know that Q.2 radiation is equal to minus Q.2 convection. Why? Based on the energy balance that we wrote for surface 2. We have two surfaces with emissivities, so we have two surface resistances, as simple as that. And since there is just one space between these two surfaces, so we have just one space resistances. So two surface resistances, we have two emissivity, two surfaces enclosure, both, so we have just one space resistances. So Q.2 radiation is equal to minus Q.1 and 2 radiation. From we just explained it previously from page 786 of the textbook, and two surfaces enclosure, which will be equal to minus Q.2 and convection. Okay. So let's say sigma, sorry, this is not this one, we just like have this. Okay, so now how we can find Q.1 and 2 radiation? Very simple. Sigma T1 to the power of 4 minus T2 to the power of 4 divided by 1 minus epsilon 1 A1 plus 1 A1 F12 plus 1 minus epsilon 2 A2. Okay, you remember that? So this is basically is Q dot 1 2 radiation. How about this? Basically this is equal to H A2 T2 minus T infinity. Okay, so now let's do and calculate it. Okay, so it's we just like let me just write it down one more time. So here just that sigma T1 to the power of 4 minus T2 to the power of 4 minus epsilon 1 A1 epsilon 1 plus 1 A1 F1 2 minus epsilon 2 A2. This is equal to H A2 T2 minus T infinity, or Tm basically. Okay, so from here what we have the Stefan Boltzmann, we have the temperature of surface 1, which is 1000. This T2 we don't have it. H we just calculated it. T2 again we don't have it. Tm we have it is 400 Kelvin. Epsilon 1 we have it. Epsilon 2 we have it. And F12. Okay, so to calculate the VU factor, we say that okay, F11 plus F12 is equal to 1. Very simple. F11 is 0, plane surface, so F12 is equal to 1. We have calculated that easily. A1 was equal to 2R0L, A2 is equal to PROL. So we just like put it inside, and if we add all those numbers that we have and these correlations into, we can get T2 of 696 Kelvin. Okay, so we find this one. We found the second part of the question, because if you remember, the question was asking what is the temperature of the insulated surface. Basically it was asking for T2. So if the T1 is maintained as at 1000 Kelvin, what would be the temperature, the surface temperature of surface 2, which is well insulated? So we find it, 696 Kelvin. Now if we go back to here, you remember we have H, we find T, so easily we can find the first question was asked, what is the rate at which heat must be supplied per unit length to maintain the plane surface at 1000 Kelvin? So let's just write it down one more time, and after that just put the numbers that we have and all will be fine. So Q.1 ext divided by L is equal to H pi R T2 minus Tm plus H2R or T1 minus Tm. T1 is 1000 Kelvin. T2 we just calculated 696 Kelvin. Tm is given 400 Kelvin. How about H? We just like calculated it, which was 66.2. But here let me explain something that a lot of students make a mistake. For example, H, if you write it here 66.2, you won't get any mark for it. You know why? Why? Because we don't have such a thing in mechanical engineering. Numbers should come with units, okay? What is the unit of convection heat transfer coefficient? Watt M2K. Okay, so now we have all those numbers. We know the pi, RO, we have it. So if we put everything into the correlation, the final answer for Q dot 1 ext divided by L is equal to 2820 watt per meter. Okay, so you see how simple it was. By using the concept of convection, a little bit of manipulation when we used the energy balances. After that, a little bit of knowledge from convection, heat transfer, we sorted out. Why? Because the convection, we know that it's easily is HA, the temperature difference. The only problem we might have is calculating H, which is heat transfer coefficient, but we also know that it's related to K, Nusselt and Prandtl number and Reynolds number, and we can find all those correlations, and it's a little bit of work, but it's not complicated, far from complicated, but of course needs a little bit of work. Okay, it was one example to show you how convection or even conduction might affect the energy balance, and it's not just all about radiation. You need to be able to calculate when there is like a convection or conduction. I solved one example for it to give you some kind of like an understanding what is happening. The textbook also talks a little bit about the effect of radiation on temperature measurements, because that might will affect the measurement as well. But instead of like explaining it, I'm just like going to solve one example and explain about it while I'm solving the example. It's question 13.139 of your textbook, saying that thermocouple used to measure the temperature of hot air flowing in a dock whose walls are maintained at TW 500 Kelvin shows a temperature reading of 850, assuming the emissivity of the thermocouple junction to be 0.6 and the convection heat transfer coefficient is given. Determine the actual temperature of air. So basically, when a thermometer or thermocouple, whatever, is placed in a medium, heat transfer takes place between the sensor of that thermometer and the medium by convection until the sensor reaches the temperature of the medium. On the other hand, when the sensor is surrounded by surfaces that are at a different temperature than the fluid, radiation also takes place. Why? Because of the temperature difference between sensor and the surrounding surfaces. When the heat transfer by convection and radiation balances each other, the sensor indicates a temperature that falls between the fluid and surface temperatures. Let's balance it and see how does it work. For example, H, we spoke about convection, Tf minus Th is equal to epsilon sigma Th minus Tw to the power of 4. What is Tw here? Let's go here. Tw is a surface temperature always. So surface temperature. What is Th? Thermocouple. Couple temperature. What about F? Fluid temperature. Okay, so basically that's the balance between radiation and convection heat transfer. So if we want to find the actual temperature of air or fluid here, Tf is TTH plus epsilon sigma TTH to the power of 4 minus TW to the power of 4 divided by H. So Tf, the actual temperature of the fluid, TTH, measured temperature by thermometer or thermocouple, TW, temperature of surrounding surfaces, and H is the convection heat transfer coefficient. Okay, so you can use this correlation for all the questions related to the effect of radiation on temperature measurement, but in this specific case, if we put it like as I mentioned, Tf is equal to TTH plus sigma TH to the power of 4 minus TW to the power of 4 divided by H. We have all those numbers, so Tf will be 1000 Kelvin, 1111 Kelvin. What is Tf here? We mentioned actual temperature of the fluid. In this case, the actual temperature of air. Okay, thank you for your attention, and that was it for today. So it's like section 1 and section 2. I just divided into two sections. In this section I solved two examples to give you a better understanding, and with this lecture we finished 2 chapters of a textbook on radiation, and please go through it and read chapter 12, 13, and be ready for your test. Good luck with the test. Okay, enjoy the rest of your day. Bye bye.